how it's going to benefit for the applications. So this is just we are planning, right? It's not yet used in the practical, right?
Yes, sir. It's very start stage, sir. That's it, sir.
Okay, ma'am. Okay.
Yeah. Thank you, sir. Thank you, sir.
I don't know, ma'am. If you have any questions, please, ma'am.
No, sir. We can move to the next presentation.
Okay, ma'am. Okay.
Yeah.
Thank you, ma'am.
Thank you, sir. Thank you, ma'am. Thank you, sir.
You can move
I'll
to
stop sharing.
Sure.
Thank you, ma'am.
Sure.
Hello.
Yes, ma'am. We can hear you, but we are not seeing your presentation, ma'am.
So, dear participants, so next participant, Sindhu ma'am, are you there? Sindhu Shah.
Uma ma'am.
Sir?
Okay. I think maybe we can move to the next presentation. Maybe.
Yes. So next presentation is by Gopala Satish Kumar. Sir, you can press the phone.
Yeah, I think we can see his presentation.
Hello, am I audible, ma'am?
Yes, sir, you are audible. You can go ahead.
afternoon, sir. I am Gopala Srishkumar from Department of Pharmacy, Autonomous University. My presentation title is Confirmation of Best Method for the Extraction of Antioxidant Compounds from Cucumis mellow subspecies Xrd leaves.
Hello, Gopal Srishkumar. 1 minute.
Yes, madam.
Sir, kindly share your full screen.
Madam, my mobile not supported, madam.
Okay, sir. You can go ahead, sir. Thank you.
Okay, thank you, madam. Thank you. Introduction. In 2000 BC, people ate the parts of plants to cure the disease. In 1850 AD, drink the portion of the plants, and after 1940 AD, they swallow the synthetic pills for the treatment. But in 2000 AD, again, people start eating the parts of plant to cure the diseases because synthetic pills produces some unwanted side effects. The activity of the herbal medicines is mainly by the presence of phytochemicals, for example, alkaloids, flavonoids, steroids, terpenoids, tridenides, saponins, tannins, and phenolic acids. The antioxidants are important in life because the most of the diseases are caused by the free radicals, which are scavenged by the antioxidant. Extraction and identification of medicinal compounds is play an important role in medicinal research. Many extraction methods are involved in the extraction of vital conditions, so that the confirmation of best method for the extraction is important. In this research, focused on identification of best method for the extraction of antioxidant compounds from Cucumis mellow Xrd leaves. This is the plant profile. Cucumis mellow subspecies Xrd aerial parts. This plant is also known in English known as wild muskmelon, and in Tamil Mirkanchadi or Chukkuvelari or Chukanjadi. In Hindi name Kachari, Telugu Tasakaya. Scientific classification, this is under the Cucurbitaceae family. Distribution is widely distributed in African and Asian countries. In India, Punjab, Himachal Pradesh, Haryana, Rajasthan, and Tamil Nadu, Kerala. Bioactive compounds, flavonoids, alkaloids, steroids, and tridenides. Medicinal properties, fruits having the anti-hyperlipidemic and treatment for burns and operations. Seeds having anti-tussive, antioxidant, and digestive activity. Seed oil extract having antifungal activity. Leaves having anti-rheumatoid and antioxidant activity. Methodology. The plant material was collected from the area of Pungavanatham, Thuthukudi district, and authenticated by Dr. N. Srinivasan, Department of Pharmacy, and Professor of Pharmacognosy, Annamalai University. The authentication number is PCOL 2021-002. The extraction method, various extraction methods are involved, such as cold maceration, hot filtration, refrigeration, oxide extraction, ultrasound extraction, and also certification extraction method. And the total phenolic and flavonoid compound is estimated by using spectroscopical methods, and also in vitro antioxidant studies were carried out by using APGS scavenging assay and the TPPH assay. Result and discussion. The table 1 shows the percentage yield for the various extraction methods. For maceration, I got 11.95 weight per percentage of weight per weight, and hot filtration I got 12.10, and reflex condensation 20.22, and the oxide extraction 17.37, ultrasound sonication 29% weight per weight yield. In this, the extraction yield is very higher in ultrasound sonication method, but less in maceration method. Total phenolic content. The total phenolic content is estimated by using spectroscopic method, by using Pauling capillary method, and results of the phenolic content. Maceration method 21.83, and hot filtration method 17.78, reflection condenser method 18.06, Starklet extraction method 77.82, ultrasound sonication method 12.08. In this method, total phenolic content, Starklet extraction having the higher phenolic content. Phenolic contents are the main antioxidant compounds, so that I estimated the phenolic and flavonoid contents. total flavonoid content. In total flavonoid content, also the phosphate extraction method having a higher total flavonoid content, 30.06, and the ultrasound solidification method having the 9.47 percentage only. But percentage yield compared to all the extraction method, ultrasound solidification method having the higher yield. But total phenolic and total flavonoid content, phosphate extraction having the more amount of phytocontent like flavonoids and phenolic compounds. So that phosphate extraction method may be having the higher amount of antioxidant compounds. And also I have estimated the antioxidant capacities by various in vitro methods, including TPPH assay and APGS assay methods. In APGS assay methods, maturation method having the 11.78 microgram per ml of IC50 values, and hot filtration having the 10.88, reflux condensation 13.23, phosphate extraction 9.04, ultrasound solidification 10.65, and the standard quercetin 6.50. Compared to all the extract, phosphate extraction having the low IC50 value, so that it is having the higher antioxidant activity, which is compared to standard quercetin. It is likely similar to the phosphate extraction method. And also the TPPH assay also maturation activity, maturation method 19.85, and the hot filtration method 21.25, reflux condensation 20.33, phosphate extraction 18.46, ultrasound desonification method 21.08, and standard quercetin 5.74. This also having the phosphate extraction method only having the higher antioxidant activity. In conclusion, in this research we concluded that phosphate extraction method is best for the extraction of antioxidant compounds from Cucumis megavar agerestis leaves. These are my references. Thank you.
Thank you, Gopala Satish Kumar. I think so that your research is just only comparing the methods, how to extract.
Yes,
okay, I think what about your future plans?
Future plans is I am isolating the compounds responsible for antioxidant activity, and also perform the animal studies to find out the mechanism of action, exact mechanism, and also perform the molecular mechanism.
I think it would be nice to use them for the actual studies. You know, the extraction is fine. I think you have a good comparative study in different methods, methods of the method, especially you are showing the yield. And also one is the yield is not that different from one to other techniques, like it's the percentage is too close to each other. And maybe I feel that apart from this, maybe you need to use your material in order to study the actual problems. Okay.
Yes.
Good. Thank
So
you.
actually, okay.
Yeah.
So actually, hello. So
yeah,
actually,
I can hear you.
Actually, in small scale, we can find out the small amount of extraction, and also small difference means in large scale it may be the higher differentiation.
Okay. Okay, I understand.
Okay. Thank you. Thanks.
Thank you. Thank you.
Thank you, sir. Thank you.
Sabri sir, we can move to the next presentation.
Sure.
Stop the presentation, sir.
Sure. Gopal.
Thank you. Thanks.
Good afternoon, dear Star and Madam. So I am the next person. So myself, K. Kandasamy.
Welcome.
Thank you, sir.
We are not seeing your presentation. Yeah. It's loading.
Just a minute, sir. Yeah. So it is visible one.
Yeah, yeah, yes, yes.
Yeah, thank you very much. On behalf of Chicana Government Arts College, so I thank you everyone for the opportunity to me. So my presentation is eco-friendly ultrasonic wave synthesis, categorization, and corrosion inhibition activity of CDS quantum dots. So, some introduction. Low dimensional semiconductor quantum dots have unique properties such as photodegradation, anti-corrosion, and biosensing compared to their high dimensional quantum dots. The chemicals in this method are complicated due to the cost effective, slow rate of reaction, low yield, and risky in human health concern. Synthesis of the CDS quantum dots is a major challenges through the green synthetic protocol. So natural plant and as well as the agricultural waste is best used for the deep the and stabilizing and capping agent for the preparation of quantum dots because of its better combo biocompatibility and environmentally and cost effective. Plant extract contain the remarkable organic capping agents like cellulose, carbohydrate, proteins, pectin, and vitamin, etc. Especially the Dilodus electa plant leaves has rich source of flavonoids, terpenoids, steroids, and proteins. So these molecules have major functional groups such as the amines, carbohydrate, and hydroxyl groups. The present work reports a facial and a green sonochemical approach for the synthesis of CDS quantum dots using a Lilonus electa plant leaves water extract as a capping and stabilizing agent. We have made an attempt to synthesize CDS quantum dots using eco-friendly and naturally renewable sources such as Lilonus electa plant leaves extract as a green template. The effect of phytochemical content on the particle size, morphology, crystalline behavior, elemental distribution of the synthesized CDS quantum dots has been reported. The corrosion inhibition performance of the CDS quantum dots corrosion inhibitor was tested in the presence of electrolyte medium, namely 1 mole HCl, 6 mole KOH, and is 0.5% of NaCl. The Tafel plate polarization curve shows that the corrosion rate of the zinc plate reduced when the plate were coated with the CDS quantum dot under hot aqueous electrolyte, particularly at 3.5% of NaCl medium. The experimental details, especially the preparation of the corrosion inhibitor CDS quantum dots corrosion inhibitor. So around 6.1 gram of CDS quantum cadmium chloride, approximately 0.2 mole was added into the 100 ml of Lilonus electa leaf extract. And dropite graph Na2 sodium sulfide added dropite graph into the Lilonus electa water extract. The formation of the CDS is indicated by the orange yellow color precipitate. The above solution was around 30 minutes at room temperature, and then followed by the high intensity ultrasonic probe was used to position the solution in ultrasonic reactor, which was summarized around 1 hour. And ultrasonic wave treatment has been administered until the defined suspension was achieved. The prepared suspension of CDS quantum dots corrosion inhibitor were separated by ultracentrifugation, and then the CDS quantum dots were then washed several times using DE water as well as the absolute ethanol and dried at around 12 hours at 120 degrees Celsius. So these are the results. The figure 1A indicates the Xrd analysis of the CDS quantum dots. It's a cubic phase which are indexed with the 111, 220, 220, 311, and 331 planes. So it's say JCPDS file call number is 10.0454. So through the D5 formula was used to measure the average crystalline size around 4 to 5 nanometers. Total from the Xrd result data suggestion gives the CDS corrosion inhibitor diffraction peaks match the exact quantum dot size, and then the figure 1B shows the FTIR peaks of CDS quantum dots. The peaks at 1000 601 centimeter indicates the presence of C double bond O, and 1384 centimeters shows the CH bending, and 1235 centimeters shows the aromatic C single bond O, and excess especially 620 meters 620 centimeters shows the formation of the CDS quantum dots. So remaining the 532 seed single bond bromine structure. So then third one, the DLSS studies. From the DLSS studies, the prepared CDS quantum dots measured the mean crystalline size of the CDS quantum dots is around 10.43 nanometers. Which is agreement with the Xrd image. And fourth one, the figure 1B shows the UV spectrum of optical spectrum of CDS quantum dots. The typical absorption band around lambda max at 418 nanometers. Band at 418 nanometer indicate the exactly CDS quantum dots with the quantum confinement range and have purely spherical shape. And figure 2 and the figure B, the indirect and direct band gap energy of CDS quantum dots. So around indirect means the 3.06 electron volt, and direct means 2.96 electron volts. Is calculated through the TACO flat through the TACO flat. And the figure 1C shows the results of CDS quantum dots. So it's around exactly the spherical shape. So average diameter is 3 to 5 nanometers. It's also confirmed the Xrd analysis approximately the 500 nanometer image. This also shows the size of the quantum dots is 3 to 5 nanometer and exactly the spherical shape. So next, the about debullition, the XRF analysis of CDS and sulfur. It shows us the CDS approximately 82.012%, as well as the sulfur 17.283%. The index term transmission result shows the overall synthesized nanoparticles are constructed entirely of CDS quantum dots and have purity of 99.2%. The figure 3, the Tafel curve of 1 mole HCl and 3.5% NaCl and 6-pole potassium hydroxide. The figure 1 and figure A and B and C. So all the 3 peaks. So compared to the pure zinc metal sheet, the potential of CDS quantum dots corrosion inhibitor zinc sheet value is migrated towards the more anodic region. So from this above result, 3.5% of the NaCl give better result compared to the other electrolytes. The figure debullition 2, so comparative value of the Tafel curve. We are to the result from the Tafel through the Tafel plot. And debullition 3 is a comparative result already previously published work 1. So I compared with the other result. So compared to others, so especially so all the 1 mole HCl, 3.5 NaCl, 6 mole KOH gave better result. So the above team, so compared to the all the threes, the 3.5% of NaCl give better result is exactly 94.72. So this is a good result one. So my conclusion is in this result, the small crystalline size 3 to 5 nanometer serious quantum dots synthesis using environmentally friendly protocols using the data leads biocapping and stabilizing agent. The ultrasonic waves influence the semiconductor quantum dot synthesis challenges alternative methods to the hot injection and chemical synthesis. The serious quantum dots with the high corrosion inhibition activities that are ultrasonic small size and chemically stable have been synthesized in the short period of time. In the corrosion protection area, the CDS quantum dots corrosion inhibitor coated zinc plate combined has shown to be an outstanding anti-corrosion inhibitor in the 1 mole HCl and 3.54% NaCl and 6 mole KOS electrolyte medium, particularly at 3.5 NaCl medium, are produce highly fat corrosion protection. So these are the reference I used to compare my works. And finally, thank you very much for given a better opportunity.
Thank you, Kandasamy. I think it's a good presentation.
Thank you very much, sir.
But again, I can feel that it's just a synthesis procedure, right?
Sir, pardon?
Sir, I couldn't get
After your
you.
presentation, I think what you have presented is the synthesis procedure.
Yeah, my synthesis is through the CDS quantum dot synthesis through the green protocol via the ultrasonic wave method.
Yeah, I think it would be nice to show some applications.
Yeah, it's a very good application in corrosion inhibitors.
Okay, do you have any results from that?
Yeah, there's a Tafel plot shows the better results. So the Tafel's curve, the potential dynamic polarization measurement.
Okay.
That measurement gives better result. Confirm the corrosion inhibitor result.
Okay. Good.
Thank you, sir.
Is JP Debashri is ready?
Yes, sir, I'm ready.
Yeah.
Shall I present my screen, sir?
Yes, ma'am.
Okay, thank you.
Ma'am, we are not seeing your presentation, ma'am. Yeah, it's loading now. Yes, okay.
Sir, you able to see my presentation?
Not yet. I think it's loading, it seems.
Ma'am? Sorry, ma'am, I'm not able to hear you. Yeah, ma'am, I think I'm not sure what happened. I'm not able to share it. Thank you, ma'am. Okay, a warm good afternoon to everybody present here. Myself, I'm Dr. J.P. Divishri. I'm working as an assistant professor at the Department of Physics, PhD at Krishna College for Women. The topic which I'm going to present today is anti-biofilm activity of bismuth oxide, synthesis by solvothermal method against acetobacterial Baumannii, that is A. Baumannii, and methylene-resistant Staphylococcus aureus. We call it as an MRSA. And next slide, please. Basic principle of why I've included photocatalyst as a basic principle here is basically for the eradication of biofilm. The study started with the photocatalyst. So the materials which were a very good photocatalytic material were also showed actually very positive results when they were actually checked for biofilm eradication. So we know the basic principle of photocatalysis is like photo excitation occurs as long as the energy of the incident photon is greater than the band gap. So what happens is actually like a lot of generated we have after the reaction process we get localized holes. They react with hydroxyl ions through electron transfer and form hydroxyl radicals. And also we the oxygen reacts with the surface oxygen. It reacts and superoxide radicals are being formed. So these radicals act as the scavengers, and they further what they do is they degrade the dye particles into carbon dioxide and water. So this is the basic process of photocatalyst, where the chemicals is being degraded into green materials. So the same principle was actually studied for the eradication of biofilm as well. Now, next slide. Next slide, ma'am.
It is shown, ma'am.
Yeah. Okay. So coming to biofilm. So what is actually biofilm? It is a group of microorganisms in which the cells stick to each other and often to the surface. So then normally we can see biofilms are sticking very strong to any particular surface. So what happens is actually we can see here the 5 stages of biofilm development is seen. So the stage 1, it just started, it just go and sticks to the surface. And what happens is like it grows into a big mass here. So when it goes to the stage 5, it becomes very, very difficult to remove the biofilm from any any surface to which it is stuck. So normally, when we normally we hear elders saying like, no, don't take children to hospital; they get infected very fast. So that is actually called as nosocomial infections, which is hospital acquired. So especially these biofilms, we can find it in hospital environment, especially where the catheters which are used for patients in ICU. So a study says that in that particular catheter, the patients die because of this biofilm formation or infections more than the disease for which they were admitted in the hospital. So the most common pathogens that cause this infection is Staphylococcus aureus, Pseudomonas, and E. coli. And one important thing is these biofilms have a very good antibiotic resistance. Because they have a very extracellular, external layer is very strong, because so it is very difficult for any antibiotic to actually penetrate the surface and go inside and attack this biofilm causing pathogens. So some examples of biofilm infections is also given here. So there are given 8 examples here. Because they are antibiotic resistance, it is very difficult to treat them. Next slide, ma'am. So how do we eradicate this biofilm? We can create coating, which is antimicrobial or non-biofouling. So surface modifications can be done, or bacteriophage technique can be used. We can choose any virus that infected bacteria. And it became essential to improve the penetrative capacities. As I told you, to penetrate, to go inside the thick cell and to attack the pathogens, we need more improved penetrative things. And bismuth nanoparticles were found to inhibit bacterial growth in antifungal activity. So this was the base for a study to take bismuth oxide for this study. Next slide. So the objectives of the study is to prepare bismuth oxide by solvothermal method and compare the experimental values with theoretical results, to study the structural and morphological properties, and as an application for biofilm eradication. Okay. So talking about bismuth oxide, the band gap is in visible range. It is basically because of the interaction between the 6s bismuth and O2p orbitals, and 3 phases actually has tetragonal zircon, monoclinic scheelite, and tetragonal scheelite. But after a lot of studies, it was found that the monoclinic scheelite is actually best for photocatalytic application, because it has a BiO polyhedron, which is more distorted by the 6s2 lone pair of Bi3 plus electrons, and it is a direct band gap semiconductor. Next slide. So this is a preparation technique. So the raw materials used were bismuth nitrate pentahydride and ammonium metavanadate. So they were actually stirred for 30 minutes. The pH was maintained at 7. It was autoclaved at 80 degrees Celsius for 3 hours. And after it was cooled, filtered, and washed and deionized washed with deionized water, it was dried at 80 degrees Celsius in an oven to obtain the bismuth vanadium oxide. So this is a normal solvothermal technique. Next slide, please. So coming to the computational method, the theoretical work. So we used actually Vienna AB in vitro stimulation package, which we called as VASP, and projected augmented wave PAW method was selected to optimize the structural geometry and electronic parameters. Then PEV is used to describe the exchange and correlation potential effects, which is assimilating the CGA approximation. So here we can see that the supercell consists of 16 oxygen atoms, 4 bismuth atoms, and 4 vanadium atoms, which is it matches with the experimental results what we have got. And the green, orange, and red represents the bismuth, vanadium, and oxygen atoms respectively in this supercell. So this is a pure bismuth vanadium oxide supercell which we have got after theoretical studies. Next slide. Coming to the Xrd results, so the Xrd results clearly shows that the samples were all indexed to monoclinic scheelite structure with the JCPS card number 140688, and we can see that no diffraction peak of any other phases were found, so no impurities were detected in this, and we tried to calculate the crystalline size using Scherer equation. So the crystalline size was in the nanometer of 15.39. Slide. So coming to the electronic structure, this is again the theoretical study. So it was evaluated using HSE06 hybrid method. This is a theoretical software for calculating the band gap. But when we calculated the band gap using the theoretical studies, it showed around 3.06 electron volt, but the experimental value is very less, which is 1.48. So when we checked with the previous journals, also the same similar results was obtained, but because we use this HSE06 hybrid method, there is a slight overrated value of the band gap. And we can see from this the second diagram, the valence band maximum VBM of bismuth vanadium oxide is mainly due to the contribution of O2p states and with minor Bi6s states. But the conduction band, we can see that there is a little contribution of bismuth, and it is mainly due to the vanadium 3+ states, and we can also see that which could be due to the transition of this under visible light irradiation. This difference is between this. So in this second diagram itself, the left hand side shows the valence band maximum and the right hand side shows the conduction band maximum. So we can see the difference in the valence band and conduction band. Next slide. So optical properties, we can infer that the optical absorptions is in the range, where lambda is more than 380 nanometer, which corresponds to the visible light spectra. Next slide, ma'am. So we can confirm that in the visible light region itself, this acts as a very good absorption. The absorption activity of bismuth vanadium oxide is more in the visible light range itself. And next slide. So coming to the valence band maximum and conduction band maximum, we can see that here in the figure A is actually the VBM charge density. It consists of filled oxygen p orbitals. So as we already told, the red one is the oxygen, orange is vanadium, and the green is bismuth. And the CBM, that is conduction band maximum charge density, major contribution is vanadium d orbitals. This also evidences our previous results, and the delocalized nature charge density states would help in good migration of photogenerated electrons and holes to the surface, which further enhances the photocatalytic and also the biofilm eradication of bismuth vanadium oxide. Next slide. So coming to the Scm micrograph, so both the micrograph are of the bismuth vanadium oxide. So we can see in the second image, the acicular sheet structure is clearly visible. The uniform particle size and shape distribution is depicted in the Scm figure. So with high magnification, we can see a beautifully acicular sheet structure of the sample was observed. Next slide. So strains and type use, I'm not going to explain the complete thing. So the pathogens which we have chosen is A. baumannii and MRSA, and we have obtained this from Institute of Microbial Technology, Chandigarh. The screening was done using Congo red agar and tube method, and the antimicrobial efficacy was done using agar-well diffusion method using Muller-Hilton agar. Bath assay, that is effect of bismuth vanadium oxide on hydrophobicity, was done using Bath assay, and anti-adhesive assay, that is inhibitory effect of bismuth vanadium oxide at different concentrations were done, and the broad dilution method, again to find out the minimum inhibitory concentration, was done using the broad dilution method. Next slide, ma'am. So coming to the screening method, we can see here the black qualities which are found in the first figure, and in the second one, the violet ring which is formed. It confirms the actually the formation of biofilm of MRSA and A. baumannii. So this is for screening of biofilm to confirm that the biofilms are formed. Next slide, ma'am. Coming to the antibacterial activity, so we can see that from the values, the maximum zone of inhibition is 16 mm for 500 μg per ml of bismuth vanadium oxide, whereas minimum zone was 9 mm at 100 μg per ml. So for when bismuth vanadium oxide was added from 100 to 500, we can see that the zone of inhibition was actually growing for A. baumannii, and for MRSA, we can see that for 100, the zone of inhibition was not available, but then it increased and it reached around 15 mm when 500 μg per ml was added. Next slide. So this is phenotypic detection of SLIM formation. So we can see very clearly that the black colonies were completely are not present in the second image. So it is very clear. This is with 700 mg per ml of bismuth oxide. So the first one is for A Baumani and the second one is for MRSA. Next slide. So here we can see that the catheters were actually, the biofilm formed catheters were shown in the figure in A and C. So, and in B and D, we can see that visibly reduction of the biofilms could be seen. With 300 mg per ml of bismuth oxide was treated, this visible reduction of biofilm was formed. So this clearly says that biofilm, bismuth oxide is a potential agent for biofilm eradication. Next slide. So conclusions: monoclinic bismuth oxide was prepared using solvothermal method. The experimental results were confirmed using theoretical studies, and the sample was effective in eradicating biofilm formation. So further work is underway to inhibit the possible recombination of charge carriers and to improve the adsorption ability. Next slide. I've included a few references which has helped our work. Thank you all.
Debashri ma'am.
Yes, sir.
I think it's a complete and impressive work.
Thank you so much, sir.
Actually, do you already published this, or you are going to publish?
Sir, I'm actually in the process of publishing this result, sir.
I think it's a complete work. I can feel that you have knocked all the possibilities. I think it's really nice, impressive.
Thank you so much, sir. Thank you.
Thank you, ma'am. And also, maybe, are you a biologist? Because I can see some computation as well. Are you doing some?
No, sir. I'm actually a physicist. Yeah, and this work, sorry to interrupt, this work is actually, we are doing a collaborative work with an Shansei laboratory there in Taiwan. So one of my junior has actually helped me with this theoretical studies.
Oh, nice. Good.
Thank you, sir.
Good afternoon, all. Can you hear me?
Yes, ma'am, we can hear you, ma'am.
Yeah, thank you. Yeah? Yeah, it is a short presentation. Yeah. I hope you all can see my slide.
Yes, ma'am.
Yeah. Good afternoon once again. My name is Meena Bishan. And for today's topic, I'll be discussing regarding the influence of choice of precursors on the properties of titanium dioxide nanoparticles as photoanodes in dye-sensitized solar cells. So, now, currently I'm working in Science and Humanities Department of Providence College of Engineering, Kerala. I have done this work from Loyola Institute of Frontier Energy, Loyola College. So, as we have less time, I have made my slides in a very crisp way. As I've worked in dye-sensitized solar cells, that everyone knows that it has become an incredible alternate to solid-state PN junction device for boosting the solar photon conversion due to its low cost of materials and simple manufacturing procedures. So in this present work, what I have done is, my main objective of the present work is to investigate the effect of 3 different precursors using solvents in 3 different precursors in solvent synthesis of TiO2 nanoparticles. So throughout the presentation, I will be denoting the names as T1, T2, and T3, where T1 will be the TiO2 nanoparticles, which I have synthesized using titanium isopropoxide. T2 is the TiO2 nanoparticles, which I have prepared using the titanium oxide as precursor. And T3 will be the TiO2 nanoparticles, which I have synthesized using potassium titanium oxalate. I followed a short solvent synthesis. So the procedure is given as a flowchart here. First, all the procedures, all the conditions I have used is the same. The only thing is that I have just changed the precursors. So the precursors, so here the primary solvent, it is added dropwise to dropwise, and NH3 is added to it, and it is stirred vigorously and is stirred for 24 hours. Then you will get the gel, and this gel is washed and filtered, and it is dried at 80 degrees Celsius for 5 hours and calcined at 500 degrees Celsius to get our TiO2 nanoparticles. So based on each precursors, I have got T1, T2, and T3 nanoparticles. In this slide, I'm showing the Xrd of what I have done. You can see the Xrd peaks. It is following JCPDS number 1272, and if we compare the peaks, we can say that the full width half maximum peak intensity is smaller and broader for T2 nanoparticles. And if I'm comparing the average crystallized size, which I have calculated using the Bayes-Schroeder formula, we can see different crystallized size for T1, T2, and T3, and the corresponding peaks and planes also I have demonstrated in the chart. Okay, so as the crystalline peaks are very sharp, we can say that the particles are crystalline, shows the crystallite nature. So this is the Fe sum. So these are the 3 different Fe sums I have got. If you can see the figure, you can see clearly that in T2 we can see distinct particle formation, that is homogeneity is more, and agglomerations, much more agglomerations are there in T1 and T3. Okay. If I want to say something regarding the morphology, there's not much things to say, but visible changes are there in the topology, and you can evidently see it from the figures. This is the corresponding index. Okay, so you can see the constituent elements in T1, T2, and T3, which are characterized by EDAX, and there is a variation in the elemental composition. Okay, the mathematical value is varying because of the influence of the precursors, and there is a small additional peak in the case of T3 because of the impurity, that is slightly because of the potassium. When we do the HRTEM, from the SEM image, I have found that this T2 is showing much distinct particle formation. So I have done TEM for T2 alone, and T2 nanoparticles have the least crystallized size and agglomeration. So that's why I have chosen it for HRTEM. So the lattice spacing between the 2 individual planes is around 0.34 nanometer, which supports D values that we have obtained in our Xrd. And you can see a spotty ring pattern, which confirms that the particle are polycrystalline in nature. In order to know regarding the surface area, I have done the beta analysis of all the 3 samples. So the textural properties is given in the table, you can see it. And when we compare the pore diameters and the pore volume and all, we can say that T2 is having the least pore diameter, which is falling in the range of mesoporous, and it is having the highest surface area and pore volume. In order to study the optical properties, we have done the UV DRS. So from the Kubelka-Monk plot, we have calculated the band gap, and the corresponding band gaps are 3.21 for T1 then 3.29 for T2 and 2.99 for T3. After that, as our application is regarding dye-sensitized solar cells, we needed to know how it will behave in field-dependent dark and photoconductivity studies. So we have done the field-dependent dark and photoconductivity. In 3 samples, it has followed an ohmic nature. Okay, so when we plot the current field graph, we can see the ohmic nature, and T2 shows a better photoconducting nature. When we are comparing the values, we can say that the photocurrent of T2 is 4-fold more than T1, and the photocurrent of T2 is 7 times fold more than T3. So what we have done is we just want to optimize the best photoanode that we have prepared. So in order to optimize it, we just compared average crystallized size, band gap, surface area, and photoconductivity values. So while comparing, we found that T2 is our best optimized sample. So after that, we have plotted that T2 as photoanode, and we have done the IV characterization studies. So after doing the IV characterization studies, we got the efficiency of around 0.1651. So the conclusion of my present study is that TiO2 nanoparticles based on 3 different precursors were synthesized using soil gel method. Then I have analyzed the crystallographic, morphological, optical, surface, and photoconducting properties. The best photoanode is optimized based on the parameters such as crystallized size, band gap, surface area, and photoconductivity studies. Then I have done the cell performance and IV characteristics of T2 photoanodes. That's all regarding my presentation. Thank you.
Thank you, ma'am, for your good presentation.
Thank you.
Ma'am, you have the photoconductivity of the three procedures. So how this is comparable with the literature?
Conductivity of?
Yeah, conductivity of it. You are showing the results in the slides, no?
Yeah.
I think so. With your combination, I think T2 is good, right?
Yeah.
So this value, how do you compare with the available literature? Is it better or compared to the available literature?
For dye-sensitized solar cells, many people are using titanium, both the T1 precursor and T2 precursors, and T3 is not that much commonly used. But for growing nano rods and nano wires, they are using the first precursor. So in order to prepare nanoparticles, spherical nanoparticles, I have felt that the second precursor is good.
Okay. Good, ma'am.
Thank you.
Good afternoon, sir. My name is Prabhu.
Sir, we are not able to see your slides, sir.
Yes, sir. Yes, I will show the PowerPoint slide.
Okay, sir. Okay, sir.
Sir, PPT is slow.
Sir, we can.
Sir, can I start my presentation?
Yes, go ahead.
Yes, sir. Yes, sir. My name is Anthony Prabhu. I am working as Assistant Professor, Department of PG Chemistry, Icnnir College, Tiruchendur. My presentation topic: supramolecular interaction of 2-hydroxychinamic acid with alpha and beta cyclotextrin. So here the selected compound is 2-hydroxyechinamic acids. It is a guest molecule. Then another 2 molecules alpha and beta cyclotextrins. These molecules has a cavity in the inside of the alpha glucose unit rings. Alpha CD has 6 glucose units, beta CD has 7 D-glucose units. Then directly go to the resultant discussion part. So UV visible and fluorescence spectral data shows in the table. The absorption maximum of 2-hydroxyechinamic acid observed at 350 nanometer, 271 and another 211 nanometer. And emission maximum observed 2 peaks at 348 and 496 nanometer. So in this table shows the concentration of CD increased, but at the same time the absorption decreased with increasing redshift in the absorption maximum, and the fluorescence emission was also redshifted with the increasing concentration of CD. So this slide shows the absorption and fluorescence spectrum of these compounds with the encapsulation of hydroxyechinamic acid molecules. So in this UV and visible spectrum, the absorbance decreased in alpha CD and beta CD, but emission intensity was gradually increased, but at the same time the emission maximum was blue shifted from 490 to 450 nanometers. So this results indicates that the 2-hydroxyechinamic acid molecule was encapsulated into the cyclotextrins cavity, and then the 2 graphs that is a product of 1 divided by concentration of CDs versus 1 divided by A minus A0 for absorption data, and 1 divided by CD concentration versus 1 divided by I minus I0. So it is a fluorescence spectrum. So these graphs getting from the Benesi-Hildebrand equations. The equation is 1 divided by A minus A0 equal to 1 divided by A dash minus A0 plus 1 divided by K into A minus A0 into CD concentrations. The next slide shows the solid state inclusion complex of 2-HCA and cyclotextrins. First one FTIR spectrum, second one powder Xrd, third one surface Scm image morphology of each isolated compounds and complexes. So in FTIR, so OH stretching frequency was appeared at around 3400 centimeter per minus 1. Then carbonyl stretching frequency around 1670 centimeter per minus 1. So this important stretching frequency is mentioned in this work. Then another one powder Xrd. So all are powder Xrd patterns appeared 2 ways be crystalline nature, but another 2 complexes powder Xrd patterns is amorphous nature. Another one Scm image. So individual compounds and complexes Scm images are different in large places, which can be seen in the Scm images. Then another one part, the theoretical studies. So in this molecule has been entered into 2 directions into the cyclotextrins cavity. First one CH double bond CH COH group entering in the CD cavity. Another one aromatic ring entering in the cavity. This is optimized structure of inclusion complex. So this structures was optimized using the Gaussian software. So the hydrogen bonding was possible between 2-HCA and cyclotextrins. So the values are indicated in this slide. Then another one theoretical data. So this one formula energy stretches of 2HCA. And theoretical data, it is a very important theoretical value. So complexation energy. The complexation energy of 2HCA alpha C minus 10.12 and 2HCA minus beta C complexation energy minus 19.09. So these are the another important values. So homo-LUMO energy, difference between homo-LUMO and LUMO energies. Then our last part, the thermodynamical values are calculated for insulated compounds and complexes. Then the conclusion of my work. So the conclusion complex was studied by absorption, fluorescence, FKR, powder Xrd image, and finally theoretically optimized the structures. Thank you.
Good work, sir.
Thank you, sir.
Thank you, sir. Thank you, sir.
Ma'am, may I audible? Hello.
Yes, sir.
Okay, and the slides are shown.
Yes, sir. We can see your slides.
Okay, thank you, sir. Okay, now myself, Bhatweshwanta Bagul, Assistant Professor, Vasantrao Naika, Science Commerce College, Sharda, District Nandurbar, Maharashtra State, from Kavitribai Nabai Chaudhary, North Maharashtra University. And my presentation topic is synthesis of silver doped cadmium telluride nanocrystals by chemical method and studies on their structural properties. Now, this work deals with the synthesis and structural characterization of silver doped AgCd nanoparticles, which were prepared by using co-precipitation method, and samples were characterized by Xrd powder diffraction. The doping concentration varies from 0.1 to 0.3% of silver atoms. Xrd diffraction techniques were employed to study the structural properties of powder samples. It was found that the samples have a hexagonal crystal structure highly oriented with HKL values of 401 plane. The size of the particle is found to be increased with increase in concentration of Ag. Now, how the precursor solution is found. Now, in the present work, raw materials used for the synthesis of silver doped AgT nanocrystals, we use cadmium acetate dihydrate 99% of AR grade, tellurium dioxide TiO2 and silver nitrate AgNO3 from LOBA as a source materials. All chemicals are used in this work without further purification. All the solutions were prepared in double distilled water, and acetone is used for glassware cleaning purpose. And for the preparation of this solution, we use the formula W is equal to MC2 divided by 1000. W is the weight of the solute in gram, M is the molecular weight in the solute per salt, C is the concentration, and Q is the quantity of solvent in ml. Now, in this way, we can prepare the different types of powder having the different concentration. Now, what is and from this flow chart, how the Ag doped nano CDT nanocrystals is prepared. At first, we can take the cadmium acetate is dissolved in a 50 ml solution. Separately, the AgNO3 is dissolved in 50 ml solution of water, distilled water, and TiO2, tellurium dioxide, is in a 50 ml mixture of distilled water. The three solutions are prepared separately and stirred at a temperature for room temperature. Now, this AgNO3 is added drop wise into the cadmium acetate solution and stirred for some time vigorous temperature. After that, it can be completely dissolved. We can add the tellurium dioxide dropwise added in the solution, that is in both the solutions, and this solution can be stirred for the 3 hours at 800 rpm, and from this we can get the precipitate, and this precipitate can be filtered, washed and drying this powder and calcinated. We can get the CD 1 - X AgXT paste. Okay, in this way we can prepare the Ag doped CDT crystals, nanocrystals, and now the results and discussion, and from this we can draw define here the X-ray diffraction spectra of Ag doped CDT nanopowders for Ag concentration 0.1, 0.2 and 0.3. And from this graph we can say that as all these peaks are increasing as the concentration is increases, then the major peak is 401 having the highest intensity, and from this is the nature of polycrystalline nature of this. Now the structure is composed of hexagonal phase of 310, 401 and 422 as preferred orientation, because this is the preferred orientation 310, 410, 422. Okay, and the index base having the hexagonal Ag7Te4 lattice with a constant A is equal to 13.48 times per minute is dominated as one of the polycrystalline in nature, and the main peak is at 32.25 degree, which is corresponding to the 4G1, which is called as the preferred orientation. Okay, and the other similar peaks can be observed at 2 theta at different degrees for these peaks, and HKL values having in this manner. Therefore, it is revealed that the presence of peak related to Ag CDT at 46.24 indicate that the presence of Ag doped CDT allow in all concentration depicted by the behavior of allow formation, even the concentration is varied. That is, we can say that as the concentration is varied, but one of the peak is there which contains the Ag doped CDT. Therefore, we can say that the Ag is doped in the CDT. And in this pattern also, we can measure that is the results match with the references with the JCPDS data cards. All these, that is this is the JCPDS data card for the Ag7Te4, for the Ag HCDT, hexagonal CDT, cubic CDT, Ag and Ag doped CDT. Okay, therefore the results of Xrd Pattern show that the formation of Ag doped CDT nanopowders. Now, from this we can analyze the different parameters, that is for the different 3 concentration 0.1, 0.2, 0.3 concentration, we can calculate the interplanar distance D, and the interplanar distance D, we can say that here the interplanar distance D decreases as the concentration increases. The lattice parameters are constant, A is equal to B or C. These are the 3 lattice parameters we can calculate it here. Now the FWHM values were calculated and the crystalline size is calculated, and from this we can say that the crystalline size is increases as the concentration increases. This crystalline size is increases in nanometer. Okay, and here is the Xrd results of Ag doped CDT powders at different concentration, that is point for X is equal to 0.1 concentration. We here the 2 theta for the different formations we get and crystal systems we get here for the corresponding MKL Miller indices. Now the conclusion: precipitation method has been used to synthesize the Ag doped CDT crystals with different concentration of Ag. Structural studies have been demonstrated the influence of Ag concentration on crystal growth of CDT in the preferred orientation, and the preferred orientations are at 310, 401 and 422 planes as preferred orientation, and the can be index based as hexagonal Ag7Te4 lattice with a constant 13.48 times per minute as a dominated as polycrystalline nature, and the increase of Ag concentration supports the Ag7Te4 growth and increase in crystalline size. Okay, thank you, sir. Hello.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, madam. Thank you, sir.
Sir, how this your route can be useful for novel applications?
Sir, the application of this now, my work is for the preparation of CDS, preparation of CDT, and agent of CDT, and for the solar cell, sir. This is used for the solar cell. Oh,
Okay, sir. Okay, sir.
okay. Thank you, sir.
Thank you, sir.
Thank you, sir.
Ma'am? Uma, ma'am?
Sir, அவ்வளவுதான் சார் இந்த செஷன்.
Okay, ma'am.
So 3 o'clock. So we are
Okay.
parting 3 o'clock. We'll be having our keynote speakers session. So please be on time. Our next keynote speaker is MB Reddy. Please be here by earlier of 5 minutes before.
Okay, ma'am.
Okay. Thank you, sir.
Okay.
So, good afternoon, participants. So, for the afternoon session, we are having Dr. M.V. Reddy sir from Canada. I would like to call upon Dr. N. Bhuvneshwari ma'am to welcome the chief guest.
Okay, thank you very much, madam, for your kind invitation and introduction. So just I would like to know my voice
The
is
forum is yours.
yeah. So my voice is audible and slide is visible. So whatever next slide, I'm able to move. Oh, slide is not moving. Okay, just one second. I'm redoing. I'm sorry for. Okay, just I'm going to. Can you activate entire window? Present scale. Yeah, I think now it is okay. Share. Whatever slide is okay. Slide is visible.
Yes, sir, we can.
Okay, okay, perfectly fine. Okay, thank you very much, madam. And then thank you, Prakash, for all the for invitation as well as head of the department. In fact, since I trained in the area of physics and chemistry, so I'm going today. I'll give you, since the conference related to the both novel materials, so that at least I'm going to cover the importance of physicist and chemist work together in the area of energy storage, okay, and conversion. In the sense that any new material, I think physicists will play an important role. In the sense that characterization, I want to do really physics is play an important role. Or suppose you want to prepare any chemical, any materials, I think you need a good chemist. That's why importance of the science means chemistry and physics play an important role in the area of energy storage. So where actually previously I think I was in Singapore. Now where the Quebec state is similar to what we have, like it is like French speaking colony state in the Canada. So again we are able to see 4 seasons. Among them I think January, February is different compared to India. So everywhere covered by ice, so that way, and also here the temperature also vary depending on the climate. Sometimes it may go to -25 degree temperature. So this is the outline of my talk. I'm going to introduce the topic, followed by how the what I call nanomaterial or new material processing and characterization, and followed by few examples. So again, I think it is very important to tell that research, I think anybody can do research. It's in the sense that we need a facilities. Apart from facility, I think with a mentorship, I think people can do. So this is my small effort have been done for the last 15-20 years. I was in NUS. So the following students have been trained in the area of nanotechnology, materials and energy, science and engineering. So many people starting from the junior college and high school student in a various category, in the sense that it's almost like 1 year part-time research people can come to do. So these are the slide clearly shows that various school students have been participated. For example, if you go to the website, more clearly it will tell that the importance of the, for example, some achievements as well, publications, etc. Similarly, junior college students and with a different type of category, that from small students from NUS, high school, etc. So again, the students are able to do presentation like us. So for example, the conferences are the good opportunities for all the people to interact. So that's why this is a conferences made them to present. In fact, you can see these are a big different type of groups, and some people are able to present in the VIP presentation. And so interestingly, and so also some few groups they're able to present at various national and international conferences. So, and also we have done some public outreach. So based on, for example, our neighbor from Indonesia, as well as local schools, and also outside the world. So these are the small groups we've been trying for the last 15 years. So the bottom groups has few people from India. I think many, I think nearly 2 to 3 people from Coimbatore. So again, I think few other recent groups have been trained in the area of material science and engineering. These are the small collaboration within the India as well as various parts of the world, and also Singapore. So again, I think today I'm going to discuss about some few examples on the novel cathode. Since the topic is the novel materials, nanomaterial, I'm going to discuss few examples on this one. And due to time limitation, I don't know how much time I have. Almost like I have another 45 minutes or 45 to 50 minutes, so that I'm going to, if time permits, some of the other examples I'm going to cover. So example, for example, supercapacitor or some photocatalysis, etc. So it is very important. We know that based on the present urbanization, the United Nations World Urbanization Prospect reports, in fact, 55% of the world populations are lives in the urban areas. It may expect to reach by 68% by 2050. In the sense, the future cities will face major challenges maintaining sustainable environment, healthy lifestyle, reduce the pollution, for example, improve the infrastructures, increasing the, and also, for example, waste management, etc., etc. Again, in the sense that if we talk about novel materials or materials, will play an important role in the area of energy, environment, water, and healthcare. I think these are the three important areas presently of interest for the worldwide researchers. So again, if you talk about the environmental problems, for example, people are talking about green energy or clean technology. We use solar, hydro, batteries, and thermal and the different type of technology people can getting the energy. So in nutshell, energy storage and conversion technology, interdisciplinary area of material science. So see here we need the importance of physicist, chemist. At the end, so if you go for large scale, we need chemical engineers and sometimes mechanical engineers and electronic engineers who work with the electric vehicles, or automobile engineers, so all work together in a system design, etc. So it is very important as a researchers. For example, many people are doing research. It is very important to understand the fundamentals and material fabrication, characterization. I think that is very important for it. So there is a way the conferences, it will give idea for you to understand how to prepare the material and characterization. These are the global energy consumptions with the different sources. You can see that the energy use, if you compare, the India is also one of the third, almost like top three highest like consumer of energy. Still, this number it may go very high, go high for the in future. So regarding that, for example, people are talking about the smart building or smart technology. So for example, always people are talking about the let's reduce the environmental pollution. So for example, if you use this, for example, batteries will play an important role in energy storage. So if you want to store solar energy or wind energy, or if you want to like run the electric vehicles, or if you are talking about the smart building or the smart cities applications, I think batteries will play an important role. So this one slide, it shows that based on the present day environment, not only in India, throughout the world, I think people are facing due to gasoline vehicles, there is a pollution. That's why we are going to replace, I think future, we are going to work on the electric vehicles and other alternative storage devices. So regarding the solar energy technology, suppose for example, so people are talking solar energy, especially places like India and Middle East, we have a huge solar energy. Again, if you want to store, we need to store the solar energy, we need a low cost and high energy density battery pack. So that's why, so again, batteries will play an important role in this direction. And some people are talking about the nanomaterials. Again, the other way you can do either by photocatalysis, water splitting technology also. We use up some nanomaterial. Again, here is very important. We need a semiconductor appropriate band gap. We can do a splitting of the water, etc. Suppose another is very important one is the people are talking about autonomous vehicles, is like driverless self-driving vehicles. Again, it will use this artificial intelligence software and LiDAR, etc. Again, the major benefit of autonomous vehicles is the lowering of the fuel consumptions and development of smart cities, for example, reduce the CO2 emission. Again, also another way is we can reduce the traffic congestion, etc. So anyway, these are the almost what they can trend they given to the in terms of revenue. So the one slide will show that not only suppose some engineers also attending for the talk. In fact, so in addition to the scientists, also again the importance of the batteries. For example, if you consider autonomous vehicles, again, we need electrical engineers, computer engineers, all and mechanical engineers. For example, you want to integrate this computer or, for example, sensors, we need electrical engineers or sometimes mechanical engineers. In the sense that if you talk about the big system design, I think all engineering, all to work together in a multidisciplinary way. So these are the different type of the opportunities. So in this area, so now I'm going to discuss about the classification of the materials. So materials are broadly classified based on the utility. They call it the building materials, or construction material, or electronic material, energetic material, or what they call as the superalloys or steels, etc. Especially today's topics. Today we are going to talk about the, I think some first day, I think first talk is given by importance of material. For example, nanomaterial is explained how the, for example, sensing applications. So that's why again the importance of the physics. If you talk about the, that's why physics will play an important role. Sometimes you want to understand physical properties or sensing properties. Physicists will play an important role. And optical properties, dielectric, and also if you talk about today, we are going to cover morely on the energy materials or what they call the energy storage or grid, etc. Again, so here importance of the so like what they call as science, etc. Suppose if we talk about the importance of the steel, I think people can use steel can construct a nice fancy building, or if you want to use with, for example, what they call as the composite materials, like carbon fiber, people can use for aerospace applications. Again, importance of the, for example, lasers, glass, optical fibers, mirrors, etc. Or if you talk about the smart windows, again, so that again it will all this one is in the area of the optics. Also, sometimes people are talking about electrochromic devices for the building. Again, it is the thin film technology by a glass substrate and electrochromic layer curve in between, and we apply the voltage and we can change the color. Advantage of this, in summary, the materials, what you talk about the novel materials or whatever the materials are needed for in terms of lot of application, not only smart building, what they call a glass, smart glasses, or flexible organic materials, or what you call as the resistive memory alloys, some sensors for LiDAR technology and graphene type material, or advanced smart materials for 5G, 6G technology. In fact, these are all the things are very important. And then smart materials for smart grid and electric vehicles and etc. So now I'm going to introduce more focus on the example. I think everybody is carrying this type of mobile phones. So mobile phone, you might have seen this type of the, once you open the battery or some battery problem, you are able to see this type of cell. I'll tell you what is there inside. So depending on the voltage, you can tell which type of chemistry, which type of material. Or later, sometimes people are using laptops. I think they maybe cylindrical cell. This type cells are put it in the depending on energy requirement. And same way in a large scale feature, if you run with the electric vehicles, I think we need a big type of battery pack. Again, if you go for electric vehicles or maybe we need a what they call a thermal management. So many things you do. Some what they call integration, especially safety, many factors we are taking into consideration. Again, materials are same. Suppose if you work with grid applications, I think we need a quadrant of the quantity. That's why. So always industry look for the materials to be low cost and easily and less toxic, etc. So it is very important if you talk about the any battery or any storage devices, it contains a positive, they call it cathode material, anode material, and there will be separators. So it is very important. So in order to do the movement, the material stick neatly. That's why we need a binder and conducting carbon. So it will improve the conductivity, and electrolyte is a medium to move the ions from one side to another side. So now I'm going to talk about some important points, like what they call a cathode and positive electrode are the same. So if you talk about lithium battery, lithium containing metal oxides. If you talk about anodes, we used a negative electrodes. So either by lithium, sodium, potassium, and carbon. And if you talk about sodium batteries, they call it sodium or potassium batteries. or sometimes we like feature the people use with calcium, zinc, and magnesium. Remember, if you go for divalent ion, because of the higher radius mobility issue, and we will get lower energy. Overall, presently, I think if you want to get high energy density, I think lithium batteries are very first one, followed by I think sodium again. So sometimes, although we will get lower energy density, cost-wise, these batteries are a little bit lower, almost 20% lower when compared to the lithium. So what they call charge is also called the oxidation, analytic scan, positive current, and discharge is also called reduction, cathodic scan, negative current. Electrolyte is a medium and to pass from, for example, nmolar, LiPFC, CDMC, ionic liquid, polymer, etc. Current collectors use copper foil for the anode, aluminum foil for the cathode. Polymer binder uses PVDF, etc. So again, I think 2019 Nobel Prize is given to the well-known chemist. I think you might have already known this particular well-known people. So for example, he's a both physicist and chemist. I think he won the Nobel Prize. In fact, he's won almost like 99 years, one of the oldest Nobel laureate. Still is active. In fact, it is I think we had a nice opportunities to work under him. In fact, I also recently some of the collaboration we did with some of the some review related to him. So in fact, that's why it is very important. In fact, his contribution in the area of the what they call as metal oxide, layered compound, etc. In addition to this one, another well-known person, Michel Armand, also the French chemist, will play an important role also to obtaining what they call rocking chair and polymer battery concept, etc. So since some students are the new, I'd like to introduce the principle, how the principle of lithium-ion batteries or what are sodium, any type of the ions is nothing but movement of the ion from the one side to cathode to anode, where the electron will pass through circuit. Again, if you watch the lithium battery or sodium or potassium, almost story is same. Only thing is that what they call as the voltages, it will vary depending on the which type of the cathode or anode we are going to use. So, for example, during charge, if you take a metal oxide, the simple voltage versus current plots, you can see that when you remove lithium from the structure, so we can get a voltage will develop. It means that we can get a plateau. So this one is called as oxidation, means cobalt 3 plus to 4 plus. Again, during discharge or reverse scan, we'll get again cobalt. This called reversible, means again 3 plus to 4 plus to 3 plus. That's why we call it the redox potential. And the same curves, if you plot this one voltage as a function of capacity by galvanostatic mode, so almost you can see nearly 3.9 plateau we can get. The same story if you work with the lithium iridium fluorophosphate, nearly 4.2 volts we can get. So in summary, if you look at the new materials or anything in terms of any energy storage or batteries, always you have to look for the higher the what they call as potential difference between the cathode charge minus discharge. That is the fundamental. That's the way you can get the high energy density. So again, if you talk about later you want to write a like a review papers or publications, so we need to write a proper mechanism. That's why in total all the battery people we broadly classified 4 type of mechanism. Among intercalation, deintercalation means we can get only one lithium going in and coming back, and in this mechanism we can get less volume variation in the sense that we don't see much expansion. For example, another type mechanism alloy based, for example, you take a silicon tin, it will form alloy with lithium. So for example, so due to this one we can get high capacity, again 4.4 lithium extra, and also another is we can get some expansion, the huge volume expansion. So this is a bit a disadvantage. Still to avoid this one, I think people have been use of nanotechnology or some different type of technology is possible. I don't have time to discuss later. I'm going to, if time permits, I'm going to discuss in a later stage. Another one is the conversion type of the oxide. For example, you take any metal oxides. So here it is more popular. So again, I'll tell you what are the little bit difficulties of this. Although we can get high capacity, again the voltage hysteresis is a major issue. So if you talk about the alloy and conversion based material, again depending on the voltage, people can do the things. So it's very important. Sometimes any new researcher or any industry people, I think they will always ask many things. Depending if it's academic researcher, okay, I'm happy. I'm getting high energy density, high capacity. I can publish. And sometimes it is very important in order to run the electric vehicles or any battery. I think it is very important you get high energy density, high capacity, and a long cycle life and more reliability in the sense once you purchase electric vehicles. I think whatever the 300 kilometers they mentioned, okay, it should be reliable and adapt the climate conditions. For example, say extreme climate like place like in Canada or like India, sometimes in summer it may go to 55-degree temperature. So that's why. So if depending on the temperature, the electrolyte conductivity will vary and also some flammable issues. That's why. So it has to work with accordingly climate conditions. Good Coulombic efficiency almost like 99%, and lower impedance means resistance of the cell. It means during charge discharge always you to get a lesser resistance is good. At the end, people like us, I think anybody wants to, it is like filling the gasoline or whatever the petrol. Is there any way to similarly just to hook that, for example, charger gun? We can charge a battery within 5 to 10 minutes. Is a question mark. So the main issue here is that due to the diffusion limitation, in the sense that it is not so easy to charge because these are solid. There is a kinetic issue. That's why, and still there is a lot of interesting things is going on with all over the world, especially industries, how to do fast charging with a different technology. So at the end, so although academic researcher this way, at the end, if industry, I think they always are industry or common man, they're always looking for the more safer material, low cost. I think cost is a major issue. That's why cost is, and also no toxicity, and it is very important in the sense that environmental, what they call a circular economy, sustainability, and recycling. I think these are very important points you have to take into consideration. So again, some other few more points I'm going to talk about the fundamentals. In again, suppose any young researcher want to do this type of batteries or any either sodium or potassium, always to look for, if you want to do this one, material should be low atomic weight automatically. So these are fundamental equation. If you theoretically you can calculate based on the number of Faraday's constant, number of lithium to the molecular weight. So in summary, for the cathodes, you have to look for the, or anodes, you look for the lower potential discharge potential, flat potential, where the cathodes higher is better. So voltage of cell is nothing but cathode minus anode. And if you talk about energy density, voltage of cells multiplied by capacity, again multiplied by current is called power density, etc. So ideal electrode materials for lithium ion batteries, it must be soluble with it is very important. It must not be soluble in the sense that if you fabricate the cells, if you sometimes your cathode or anode, it will react with electrolyte. It may not be really good. So, and also we need a good mixed ion conductors. It is very important. The electrolyte should be a mixed ion conductor. So electrolytes are the important. Suppose you talk about inorganic salts, lithium, sodium, all the thing again. So if you talk about the sodium or all type of batteries, respective salts are needed. So it's very important you have to use organic solvent. The reason is that if you use organic carbonate solvent, we can go to slightly higher voltage. If you use aqueous system, maximum we can go to 1.23 because of the decomposition of the water or what they call. Okay. So again, so these are the problems to be, although sealing and flammability issues. So that's why people have to look for the polymer electrolyte based composite again. So again, here we need a operating temperature, etc. Separators are very important components of the batteries, again to avoid short circuit. So important parameters, we take in thickness is less than 25 micrometer, porosity and high permeability and electrolyte resistance and good tensile strength. These are very important points to if you want designing the separators. Again, solid electrolytes. In fact, recently, I think there is a problem with the safety issues and then because flammability. Oh, is there any way to what they call reduce the, for example, interface flame safety issues by using solid? It means that instead of replace the liquid electrolyte by inorganic solid electrolyte. So advantage of this technique is we press the cell in a layer by making compacting. and it is almost like so again the main issue is that we look for high ion conductivity and wide potential and chemical stability, in the sense that the main issue is that we are going to heat the composite, for example cathode and electrolyte. So again it won't react with the material, and we need the important point also, thermal expansion coefficient has to match with cathode and electrolyte is very important. And good chemical stability also we take into consideration. For example, crystal structure transformation should not occur, and the sintering temperature has to match. So these are all things point to take into consideration. So in summary, so this lithium batteries, why it is more popular? Because of the lightweight and higher voltage if you compare to other type of the batteries. So some people want to, depending on the technology, we can get different type of the cathodes. So again, you can see the depending on the chemistry, you can see the thing. So how, suppose for example, people are talking about nanomaterials, the material processing and characterization is very important. So depending on the which type of the chemistry or which type of technology people are going to use, I think accordingly your physical or electrochemical properties are going to vary. So I'm telling that this is a periodic table. So if you are a physicist, or sometimes people are working with the semiconducting technology, or since we are battery, with lithium containing sample and mainly from transition metal ions. For example, these are the nickel, cobalt, manganese, and then sometimes iron, and vanadium, etc. And so we need oxygen, some cases sulfur, and then silicon, tin we can use. So anyway, we also in fact, since I am a chemist, we work with the different type of materials during for the last 20 years. I have less time to discuss about some magnetic properties also related to magnetic material, etc. So what type of depending on the applications, again, as we know that the nanomaterials are played depending on size and shapes. We can play how we can prepare by the chemical methods or physical method. Depending on recipe, we can get a respective shapes, etc. So it is very important. For example, the material processing, or what are the material synthesis and characterization techniques you can get by using chemical method, so molten salt method or solid state method. In fact, there are all the different type of chemistry with a simple beaker, with this approach you can do. Or since I'm a physicist, you have sputtering in it. You can use, you can get a thin films, or sometimes for pulsarizer. Again, some technique may be expensive. For example, MV is more expensive, especially universities or like colleges you cannot afford also. Sometimes RF sputtering can afford. For my pulse laser also, depending on the how. So again, sometimes for thin films we can at least you can do, or you can do simple what they call a sol gel or coating technique also. Again, so depending on the technology, we can use the respective thin film deposition techniques. So again, sometimes these mechanical engineers, or for example, people want to prepare the all solid state batteries, or if you work with, for example, solid oxide fuel cells, or sometimes alloys, etc. We need a what they call as a powder metallurgy techniques. I think you can use the hot press, the spark plasma sintering, etc. So it is very important. I told you that since we are a physicist, you have to characterize the material by crystal structure by using Xrd is one of the importance of the physical technique. And neutron diffraction, since you are a physicist, you are very good. I think you can do very fantastic material characterization. Or Rutherford backscattering spectroscopy. In fact, this is also more on like I think nuclear physics you are going to learn. I think nuclear reactions. These are all thin films. These are the best techniques people can use to characterize the material. So other physical and electronical characteristics, since we are working with the batteries, we need a magnetic properties, or some cases we need a battery testing. So galvanostatic cycling, etc. So another important technique, for example, if you talk about the morphology, you need a Scm, Tm, etc. So these are the various characterization techniques. Since at a time you can these are the various physical, again, importance of physicist contribution, and these are the various electroanalytical techniques. So why I'm telling that, since when I use almost like I think almost 20 years back, I used to take one the old Xrd refractometer, I used to record the sample to not take good statistics almost 24 hours. Now, due to detector technology, I think we can see the improvement in the sense that now your life is a little bit faster when compared to whatever during my time. Still, so the idea here is that so because of detector technology, I think we can do a lot of advancement. So this is very important detections you to remember is the Bragg's law. So for example, when X-ray, for example, this particular sample we are going to put here, when X-rays are incident on particular powder sample, there will be diffraction occurs. So this diffracted ray is going to be collected by using the detector. So by knowing the well-known formula 2D sin theta is equal to n lambda, finally we may get the ready-made intensity versus 2 theta patterns. So remember, if it is thin films, if it is our amorphous, we can get a broadened lines. We don't see due to the what they call no ordering and local ordering, polycrystalline and crystalline materials. So again, depending on peak position, size and shapes we can do, and also etc. and also peak intensity, everything. By knowing the full width of maxima, we can tell that your materials are nano size or nanocrystalline size. So this is one way. If without going TM, I think in average in the nanocrystalline size we can calculate by using the X-ray diffraction. So as you can see, for example, so is a typical amorphous sample. This complementary to TM, you can see the no line. If it is nanocrystalline, so you can see we get a ring, circular ring like that. Again, improved crystalline, vertical polycrystalline, you can get dot dot. So again, how we can usually use a diameter divided by 2 and 1 over d. So this d value we can closely compare to the Xrd. So that's the way we are going to index these particular things. So these are the various crystal structures we are going to use. Since I don't have time to discuss quickly, I'll go through some of the few, most of the crystal structure have been studied in this category, including not only me, all over the material researcher physicists which come under this category. So impedance spectroscopy is one of the useful techniques. So you want to understand a lot of physics. For example, you want to study the ion conduction mechanisms or solar cells or fuel cells and supercapacitor etc. Or in addition, not only this one usually, so we can get a Nyquist plot in the real and imaginary plots, and sometimes we can call board plots. And again, due to time limitations, sometimes you have to understand the particle double layer capacitance or bulk capacitance or bulk resistance and Warburg impedance, etc. These are called Warburg impedance, and this is called sometimes charge transfer resistance, etc. So the time limitation, I'm going to skip a little bit more details on the individual explanation. In fact, if later people are interested, I'm happy to discuss more details on how the how we can do modeling and how to do the equivalent electrical circuit, etc. So typically we may get, depending on if it is a cell is with a single semicircle, in the sense that without charging a battery, after charging we can get 1 to 2 semicircle. For example, charge transfer will come from here and bulk resistance. So it is very important depending on which type of materials or which type of the, for example, solar cells. Accordingly, we have to use proper explanations, and again we need a knowledge of materials, how and understanding the both chemistry and physics, etc. So since your physicists are there, how with the thin films also we can get by using this various technique. Since I don't have time to discuss, so again we can do chemical vapor or physical vapor destruction technique. Among them, RF sputtering, we can various physical parameters, we can control them composition structures. Among them, I think, for example, Rutherford backscattering is a very useful technique to know the composition thickness. Usually when the helium beam is incident on a particular thin film, by knowing the backscattered energy, so this particular the energy is there to proportional to the atomic mass. It means higher the mass, higher the what they call higher the energy channel number. So automatically we, by knowing this composition thickness, we can do by using simulation, we can know the composition thickness, etc. So again, use of the above sputting technique, either you can do all layer by layer thin film technology. So now I'm going to discuss about the what type of the materials, for example, cathodes and anode. So again, cathodes we work in the limit of 3 to 5 volts, anodes we work in the limit of, for example, 3 to 0.05 volts. So these are the various cathodes. Since I don't have had much to discuss all individually, so I'm going to tell you an example on how you can prepare metal oxides, nitrides, and carbides by using this simple tube furnace. Again, so if you want to prepare lithium batteries containing lithium containing compounds, if you want to reduce vanadium iron 3+ to 2+ here. So we need a calculated amount of carbon, mix it, and finally we can heat the sample in a particular tube furnace, and finally heat this. We'll get a respective oxides. So finally, we've been extensive, lot of materials we've been prepared. Again, sometimes people are working catalysis or chemical engineers. So there we need a metals and disperse in the carbon. So that's why accordingly, respective what they call chemistry or things, and then we have to heat the sample. You have to get a respective composites, etc. So it is very important always. So we have to look for the. So one example is the lithium vanadium fluorophosphate cathode. Again, nearly 4 volts potential and reasonably good thermal stability, etc. So this sample, since I don't have time, I told you that we prepared by using the previous carbothermal reduction method. So characterized by using Xrd. So this is the way we fabricate. You take active material PVD 70, 15, 15. Finally, we get within in NMP to make a disperse it, and with a doctor blade, and coated on the copper or aluminum foil, depending on which type of cathodes are anode, roll it and punch it, and we can get a. So finally, we are able to get a what they call as a. So the cell is ready. We can press the cells. So suppose if you want to run with a large scale with industry, I think everything is automated. So you don't need to work. So again, so the technology only we need a large scale material. So how we can fabricate the cell? You take a, for example, this type coin cell. You can take your cathode or coated material, put it here, and separator, lithium metal. Finally, cell is ready, and we can do what they call a charge discharge or electrochemical studies, etc. So the typical capacity means with cycle number or charge and discharge profile. As I mentioned that among the good cathodes, you have to look for the high potential. You can see compared to 3 cathodes, I think vanadium LiVPO4F is higher, what they call a charge potential. As a consequence, we can get high energy density. Again, we did a lot of physical techniques, for example, XC2, XRD, or sometimes we have done some in situ also recently, and Nyquist plot, etc. So again, I think very important. I think people are looking for a novel new material. In fact, among them, so there are few new materials been first time been reported in the literature. So this is metal or vanadium-based novel metal ion batteries. Again, so these are the inorganic, organic. So compared to iron phosphate, 3.5 volts, we can see nearly 4.1. In the sense that really these materials are higher voltage, we can get higher energy density. So again, we look into how the green synthesis we can prepare. We try to prepare the sample and characterize them. So interestingly, we are able to get nearly 4 volts potential or 4.1. So again, we checked a lot of the other charge discharge, and we check with impact. Suppose if you work with, for example, sodium potassium batteries, also we look again due to mobility. I told you that if you go for higher ions, mobility issue and electrolyte, so capacity is low. Still, you can see that recently, I think same like some of the materials have been relooked by other researchers, they're able to get improved performance. So some new materials we've been working with, millennium phosphate cathodes. In fact, the first example, followed by, I think after our publications, I think some of the well-known groups have been already looked into in a different way and improvement synthesis, etc. So this is one example, the lithium vanadium flow. This one also again try to prepare by sample by hydrothermal approach. Again, so we have to decompose the water. So that's why. So we have to heat the sample with respect to depending on temperature. We can get a proper different type of crystal structure we can get. So interestingly, nearly 4 volts again, and also these reversible peaks. We can see clearly that from cyclic automograms. So I told you that I discussed it with phosphate, HPO4. This is another example is HPO3. So important is that how to fabricate these cells. Again, interestingly, so again we try to prepare. These are the early first example we were reported. So interestingly, these are the charge discharge potentials. So now I'm going to, and also sometimes if you talk about the importance of chemistry, and you can do polymer precursor methods, etc. I can do. So suppose if you talk about the grid applications, for example, there sodium battery seems to be promising because again, although we can get lower energy density when compared to lithium, still in terms of cost-wise lower. So this is one example, lithium aluminum fluorophosphate. I told you that 4.2 volts. Again, if you take the sodium compounds, we can get 3. In the sense that although we can get lower energy density by using this sodium technology, still for the in terms of the cost-wise, these are a little bit 20% lower. So this is one example I'm going to discuss. So these are the Na3V2. So although reasonably we can get 3.4 potential we can get, and interestingly with our optimized carbon coating, we're able to see good rate capabilities, etc. So now I think another maybe I have another 10 minutes, so that I'm going to cover up quickly with Nano Materials. Again, people are using graphite because of the good charge discharge potentials in the lower potential. Again, we look into the graphene, fuel air graphene, and graphene, etc. So again, so importance means although we get high capacity, and the problem is these materials may not be really promising. This only graphite is a little bit good because of the potentials at the lower potential. As a layman, so any research you do, always to look for the reverse after first cycle. So any good materials always to get a capacity at the lower potential is very important. Again, people are looking to use of this graphene composite in terms of energy storage and conversion. So now I'm going to quickly detail the importance of these different type of oxides, either with nano materials. Again, among them Li40, Fi12 used in the promising material because of the lower potential of the discharge, etc. So TiO2 is one of the well-known material. I think people can use it for the different applications. For example, solar cells or photocatalysis, etc. So again, we try to prepare the sample by the molten salt approach. So again, it is more versatile method. You can try to prepare either by simple nitrate melts with titanium oxysulfate. Again, put an aluminum crucible, wash with water to remove. So again, importance of this technique, we can get high surface area. So the typical Xrd patterns, and we can see that surface area is 200 meters square, and average crystallite size also what they call as obtained by using this Xrd and closely matched with TEM. So this is one example. If you go for nano size to micron size, importance of energy storage, so nano seems to be better when compared to micron size. Suppose solar cells are one of the important things since thin film solar technology already demonstrated. So again, as academic researcher, people are concentrating on different type of the organic and disensitized, recently perovskite type solar cells. So one example, if you talk about the disensitized solar cell, again, so we can get nearly improved performance like 7.8, slight higher improved performance by using this our high surface area material. So another example is the new NB205 polymers. Again, with high surface area materials, almost we are able to get slightly improved performance. Again, we compare with impedance, always we get lower resistance. It's good to get higher, what they call as higher current density, etc. So if you talk about these perovskite solar cells, and these are the literature things, so that's why there is a different type of groups have been reported in literature. So again, each technology has been advantage, disadvantage. Again, there is a lot of challenges are there. How to make a stable material, because these materials are, so we have to prepare in a glove box, all this one you take into consideration. So again, the sensors also one of the semiconductor materials. For example, a tin oxide sensors also will play an important role. So for example, tin oxide, again, I think we can try to prepare by using the DSS applications. So what I'm telling that if you talk about the semiconducting oxides, we can use different type of chemical sensors. I think some few talks is given by already with the previous speakers. For example, you can use it for different type of, for example, different type of material. For example, yttrium stabilizes zirconium or beta alumina and then acetone type electrolyte material, etc. So again, there is a lot of opportunities, especially for physicists who want to work with the tin oxide, with N-type and P-type, different type of chemistry you can do. So in summary, use of molten salt method, we've been looking at a lot of the materials either by simple and complex oxides. So in summary, use of the molten salt approach, you can get a respective different type of morphology. So alloy-based materials, again, I told you that I briefly silicon and tin we form with alloys. That's why we can get high capacity. Again, these are the various materials we've been looking into literature. For the first time, we've been from our group. So Xrd belongs to our group. Again, importance of the discharge and charge potentials. So in summary, use of the nano size. These are novel materials we've been reported. So that's why this talk is conferences. I'm going to discuss only novel material. So again, importance of nanomaterials seems to be reasonably good. Again, we check the impedance, physicist, also we can get lower resistance. So lot of onwards have been look into some other type of the oxides. So in summary, so again, these materials. I think people can use it for the supercapacitor or some other applications also. So what I'm telling you that if you want to use this material for the applications, we have to reduce the discharge and charge potential. They're only interesting for the applications. So in summary, I think we've been looking to another type of nitride-based anodes again. So advantage of nitrides is that 3 lithium can be reacted, whereas oxides only 2 lithium. So again, we've been prepared either by simple nanotechnology, either by thin films as well as the bulk materials. Again, we're able to get a capacity. So if you talk about the in terms of storage performance, nano seems to be better when compared to the bulk material. So again, I told you that some materials, if you have good expertise, you can do electrocatalysis. I think for depending on the applications, for example, lithium air battery, I think there we need a good electrocatalyst. So again, I'm telling that sometimes air is sometimes inside the lithium, so some performance may not be really promising. Or similarly, we can work the aluminum air or zinc air, all type of chemistry we can do. So supercapacitors are simply, suppose if you have batteries, so for example, you have simple electrochemical unit, and you can do in a lab, since you need with aqueous electrolyte, you don't need expensive glow box. So depending on, for example, carbon, we can get rectangular clouds, sometimes few pseudo capacitance, for example, depending on the material, double layer, or sometimes, for example, hybrid type of electrochemical mixed together, we can do, etc. Or for example, metal oxides are the pseudo capacitance we can get by using this. So again, if you talk about lithium battery, typical curve look like again this metal oxide or supercapacitor. So again, the voltage is restricted. Only you cannot go to maximum. The voltage limit is almost like 1.2, etc. So again, use of nanotechnology or new materials, we can vary the shapes. We can do interestingly, and we can do depending on. Since I have another 2 to 5 minutes, I'm going to quickly fastly. I will go through importance of safety. Again, the safety. That's why people are getting fire with the battery at fire, or for example, some electric vehicles are from the airplanes. So safety is due to either by thermal abuse and thermal runaway. Again, so either by your charger, what they call BMS management, or malfunctional BMS management, or the problem is sometimes this voltage, two-way cells are there to everything is to monitor. If something is wrong with this BMS management, or during charge discharge, or you have material issues, for example, people went to, for example, instead of 4.2 volts or 4.3 volts, they went to the 4.6 volts. So I'll tell you what the reason is that we cannot remove the lithium very, so accordingly, if we too much remove the lithium, so there is a huge volume variation occurs, and sometimes there is oxygen release with electrolyte. Slowly, sometimes we can see some bulging of the batteries, so it clearly indicates some problem with inside the battery. That's why we need depending on materials, appropriate voltage also you take into consideration. So sometimes you can do in situ techniques like neutron, or there are the physicists we can do importance of physicist contribution. So I think last one slide, I think have another last one slide, I'm telling that importance of what they call a material recovery, in the sense that any batteries or anything, so we do material should be green, and what they call a circular economy. So this one slide clearly shows the importance of material recovery, in the sense that future predicted nearly, I think around 50 to 500 million by so electric vehicles. Again, the reach is expected to car by I think 900 million. Its total forecasted is around 11 million metric tons of the spent battery, in the sense that this so much of waste is generating. So that's why due to environmental impact rising, this, for example, what are the materials, ecotoxicity, or for example, global warming, or example, health effect again. So that's why we have to dispose the battery in a proper way, recycle. That's why these people, lot of efforts have been done with direct and different type of battery technology, vertical recycling hydro technology people can do. So again, so the more popular is a pyro and hydrometallurgy approach. So you typically, any batteries, if it is big stacks, for example, usual way is that they will discharge the batteries and dismantle it, and next is dismantling, in the sense that they remove, segregate everything. So battery pack, battery module, and battery cell. Again, pre-treatment, either thermal treatment, mechanical treatment, or chemical pre-treatment. For example, thermal means like pyrolysis, or sometimes calcination and cleaning. This is mainly what they call as the sometimes we use water-based, is a hydrometallurgy things. Again, there is a problem with the leaching. So again, each technology being advantage, disadvantage. I think most commonly people are using the pyrometallurgy because yield seems to be good and easier, and already this technology will demonstrate in the large scale applications. So these are my conclusions. Since efforts have been made and the various nano Intel, some few novel materials, and then among them I told the few materials are promising. So again, as a researcher, I always need to look for a new material, since there is also the conference title shows that new materials. I think that is very important. I agree that so if researchers to go, I think we have to look for new material. Then only at least we can contribute to the community in terms of solving the cost, and then low cost or safety, toxicity, etc. So again, I think it is very important to talk about larger scale. I think we need a cooperation between scientists and engineers. I think this is very important. And another important factors you have to take into consideration is that how to, for example, all people have to work together for the large scale applications. Again, I'm going to stop telling thank you very much, and thank you to all, and thanks for your patience, and then I'm happy to answer if you have any question and answer. Okay, thank you very much. Thank you very much. Okay, and stay safe. This is very important. I think so, and be healthy, and then and also wish you good health to you and your family members. Thank you very much. I think I can stop.
So participants, if you have any questions, you can ask to sir. Thank you, sir. Thank you for your wonderful presentation.
Sorry, I think I already, okay. Yeah, please, I think I have another 7 minutes. So if I'm 7 or 3 minutes, if it is depending on any questions, happy to answer, okay. Any simple, different, yeah.
One question.
Yeah.
I told that the lithium ion battery can be recycled.
Yeah.
So how far it is efficient, sir?
Okay, so usually not efficient. Usually recycling means as a practically I'm telling that there's a different direct method is there. So they put some small excess lithium they can do. So another way is recycle means pyrometallurgy. So it is not really again the lithium battery will land. It will come to, for example, lithium cobalt oxide. So it will not come to, if you do this recycle, that will not come to lithium cobalt. It is coming in terms of cobalt oxide plus lithium carbonate. So it is then again, if you want to use the raw materials for you prepare the material. That's all. It is not like again what they call as LiCO2. We cannot 100%. We cannot get exactly LiCO2 by recycling. Okay, remember. So it is like for example, what they call as so it is not like iron. For example, iron. So it is slightly different since two to three materials are there. So during heat sintering and heating, I think the material will decompose. So that's why there's called this. It is not like 100% recycling. It will not work. So it is like raw material. Again, we can use this raw material to prepare the batteries. That's all.
Thank you. So, participants, do we have any other questions to ask?
Yeah, I think some people have raised some more questions. Yeah. From anybody from Pandey sir, Atosh Pandey. I think they have raised. Maybe unmute and then you can answer. You can raise the question. Or anyway, if you have any questions, you can send me by. Yeah.
Sir, it's audible, sir.
Yeah, Prakash. I think Prakash also. Okay. Yeah, I know.
Yes, sir.
Thanks, Prakash.
Thank you, sir. Excellent talk, sir. Sir, is any freely available software for making impedance modeling?
Okay. Yeah. Usually, I know that presently we know that Zplot, ZView people are using. So freely available till now. If I remember, some software people have been recently. I checked some. For example, did you check with Autolab? I think they have a free software. Can you check that one? I think it will work. I'm not sure. Autolab or another software called as from biologic people. I think there is a one option is there. Okay. Yeah, maybe if I'll find out and then I can send you that. Not a problem, Prakash. Okay.
Okay, sir. Thank you, sir.
Thanks for attending. Okay. Thank you. Nice to see you all. Okay. So it is really. So in fact, Prakash also we work long back. So the life is like interesting.
Thank you, sir. Thank you very much.
Hello, sir.
Yeah. Okay.
It was a wonderful presentation.
Yeah.
I'm not from energy storage device background.
Yeah.
I'm from sensor background, sir. I would like to ask one general question.
Okay.
Is there any specific fellowship for postdoctoral researchers in Canada? If I like to do postdoctoral research in Canada, is there any specific funding agency I have to apply for it?
Now, usually that, and here also again the same story with including all the places. So maybe you discuss with the respective field with your respective professor. I think that is the only way to work. So sometimes once they agree, they will only suggest, okay, the particular, here are some fellowships are there. Again, we know that sometimes you have to write a proposal and then, that sometimes depending on the number, so like sometimes if you're lucky, we may get it, or sometimes, after 1 year, you may get a negative also. That's why, so it depends on the luck also. So the best way is that depending on the slightly your area, only you have to contact them. Sometimes always the main issue is that the many students are interested to do, because sometimes so people like very far, they have to apply for the visa. Those are all the take into consideration factors. And also sometimes you have a lot of funds and easier for them to interact with things.
Okay. The first thing is we have to apply for. I have to search for the faculty.
Yeah. Always the most is the best. Okay, we are a professor. For example, your area. So then they will only, there is a possibility like MITAC, or sometimes there is some different funding agency. Again, you have to apply again. Again, remember it will took almost 1 year the processing.
Okay.
Yeah.
Sir, thank you, ma'am. Thank you. So one question from Lavanya. Can FO3 material used in battery application?
Sorry, what is FE? FE to what?
MOO3 materials.
Okay. In fact, I quickly went to one slide in anode materials. Yes, people we've been working the MOO3, MOO2 also. So again, for example, the conversion based anode materials. I think a lot of literature people have been done. Still we can use. So since your academic research still you can publish, it's not a problem. Only the problem with this one is the voltage hysteresis. We may get a little bit very high voltage hysteresis. That's why it may not be really useful. Still, since you work with nanotechnology, I think there is opportunities. Okay, for example, so the main issue is that do you have any what they call as good tricks to reduce the voltage? For example, discharge voltage slightly lower. So that one you have to think into in terms of novelty. Still, you can do. Yeah, in simple word is yes, MO3 we can use as anode material. I think you report it in the literature. Okay, if anybody is interested, I think I'm happy to send or let them contact me by email. I can send you some papers also. Okay. I think we also done some MO2 also long back.
So one more question. They wants to know about provoked crystal structure.
Perovskite.
Perovskite's crystal structure.
Oh, okay. So anyway, again, perovskite is similar like cubic structure. So what they call as for example, in olivine, perovskite, these are all based on the minerals. So usually, I think we work on some perovskite. Perovskite is like simple cubic compound. For example, sodium chloride, okay, or olivine. These are all minerals name we've been done, okay. So it is a common name, for example, layered structure or olivine structure, or for example, spinel structure and perovskite, okay? So,
thank you, sir. So that was the question asked by Mardam. Now I thank you, sir. Thank you for your wonderful presentation, and I would like to call upon Dr. N. Bhuvaneshwari ma'am to give away the vote of thanks. Thank you, sir.
okay, thank you, madam. Thank you to all. Thank you.
Thank you, ma'am. Thank you, sir, for investing valuable time, guidance, and sharing your knowledge on advanced in nano materials for energy and conversation. We are expecting your sharing knowledge and contribution in our upcoming events also, sir. Once again, thank you for, sir.
Okay, thank you very much, and also vanakkam to all, and then okay, now okay, good evening for me. For us, almost like 6:30 in the morning. Thank you.
Thank you, sir.
Thank you. So dear participants, you can be ready for your poster presentation. So it will be started shortly.
Yeah, I'm here. Yeah, I can hear you, ma'am. Yeah. Yeah, ma'am. Okay, sure.
Yes,
I'm
ma'am.
here. Yeah, I'm here.
Ma'am, can you hear me? Because I am traveling. Okay. Shall I start, ma'am?
Yes.
Can you hear me, ma'am? Shall I start, ma'am?
Yes, Gomati, ma'am, you can start now. You can share your screen.
Ma'am. Good evening, all.
Yeah, ma'am. Yeah.
Good evening to all. Myself, Komari, Assistant Professor, Mother Catherine College for Women, 1 year body. My topic is preferred section of nickel-oxide nanoparticles by co-precipitation with effect of pH.
Gomati, ma'am, we cannot see your screen. I think the screen has not shared.
Actually, I'm traveling, ma'am.
Okay, okay, yeah, fine. Yeah.
In this work, okay.
Uma ma'am. Yeah, ma'am. Is this poster session now? Okay. Okay. So poster session means we can give them just a couple of minutes is sufficient, I think. So just they have to display their poster, no? That's it. I was thinking it's oral presentation. Yeah. Okay. Okay, ma'am. Okay. Yeah. Komati?
Yes, ma'am.
Yeah, what's your title, ma'am? What's your title you have written?
Yes, ma'am. It's a typing mistake. Sorry.
Yeah, what's your work?
Actually, ma'am, pH will be relaxed rapid of nickel oxide, ma'am. So, pH values will affect the properties of nickel, ma'am. So, and we can different pH values of nickel oxide nanoparticles.
Okay. Yeah, from the Xrd, what you have written, what you have find out? You have taken Xrd and it has not.
Ma'am, in Xrd, the average crystal size of sample is pH 23 nanometer and pH 10 for nanometer. It means pH value is increases, the particle size also increased.
Actually, you have plotted two Xrds are there, no? But
Yes,
it's difference is there. In the second Xrd plot, I think it's entirely different. Yeah, and there is no scale bar in the SEM.
Ma'am?
There is no scale bar in the SEM image. What you have confirmed from the SEM image?
Then it, I got understand, ma'am.
Yeah, your SEM images are there, no? There is no scale bar is there in your image.
Okay, ma'am. I'm not put it in the poster, ma'am, but I calculate particles.
Yeah, but the poster means the scale bar must be there. Okay.
Okay.
It's also a similar thing like a presentation. You cannot just like this. You can put some images and present it like this. Oh, so
okay, ma'am.
Okay, ma'am. Anyway, thank you. Yeah, Uma ma'am, if you have any question means you can ask her. Uma ma'am.
Yes, ma'am.
Yeah, ma'am. I think so. Ma'am. Yeah. If you have some questions, can you hear me, ma'am? Yeah.
Radha, ma'am.
Yes, ma'am. Yes, ma'am. You can't hear me? Uma ma'am? Yes, ma'am. Can you hear me? Yeah. I think everyone has network issue problem. I think so. Yeah, no. Sure, ma'am. Okay. Yes, ma'am. Yeah, let her present her poster.
Ma'am,
I
Uma
have
ma'am, I am
shared
also
my
back,
poster.
ma'am. Sorry, ma'am. Sorry, ma'am.
Ma'am, can you able to? Yes, ma'am. Yes, ma'am. I have to share my poster, or you will share my poster. I have to share my poster, or you will share my poster. Okay.
Yes, can you able to see my poster? Hello, ma'am. Yeah. Hi. Good evening to everyone. I'm Dr. Pavitra, Mother Kesri Jain College for Women, Vanyambadi. I'm in the Department of Physics. And here I showed my work on dielectric properties of BCT BST ceramics prepared by molten salt method. In this, I have chosen a lead-free material. So, lead-free material is basically having a very good environment, and at the same time, it will be showing a very high dielectric constant. So, that is why I have chosen a BCT, BST, BCT barium, calcium titanate, and the barium strontium titanate. And this I have prepared by molten salt method. And this molten salt is a very easy method to prepare a sample, and we have to take a samples in starting materials as a raw material and mixed with NaCl and KCl salt, and just directly we have to mix it in agate mortar and heat it at 1000 degrees centigrade in the conventional furnace. And after this sintering, we have to go for the sintering. So for first step, we have to do that for making a sample for formation of the sample, and next we have to make a sample as a ceramic sample. So that will be sintered in the 1250 degrees centigrade temperature. So after this, the sample will be a ceramic samples. And here I have showed this Xrd pattern and SEM images and the dielectric constant. The three images I have shown here. In this Xrd, it will be clearly shows as a cubic crystal structure, and single phase formation will be presented in prepared sample, And same images from this I have measured the particle size of the prepared sample. It's around 47 to 50 nanometer. And the dietary constant I have done with temperature versus dietary constant. In temperature, I have increased from room temperature to around 150 degrees centigrade. So at various frequencies, for example, 0.1, 1, 10, 100, 1000 kilohertz frequencies I have shown here. And from room temperature to 150, I have plotted a plot. Around 70 degrees centigrade, we'll get a shift from this peak. So from that point, we can take it as a transition point of the material. So from around 70 degrees centigrade, we'll have a transition from the phase. So tetragonal to cubic. So the sample has been transferred from tetragonal to cubic crystal phase. And this is very good in lead-free material and high dietary constant. So we are achieved as a very high dietary constant, around 14,000 dietary constant at 0.1 kilohertz frequencies. So very high dietary constant gives a high, very good in capacitance. Okay, thank you. Yes, ma'am. Thank you, ma'am. Thank you for this opportunity.
Yes, ma'am. I think instead of Pradha ma'am, I will be there, ma'am. So, Pavitra, I think you said your results are good for the capacitors. Did you able to check that? The high, maybe I think she left the meeting, I guess. Pavitra ma'am. It's okay, ma'am. Maybe we can move to the next presentation. Yeah, yes, ma'am. Yes, ma'am. Okay, ma'am. I think it's fine, ma'am. Excuse me, ma'am. I think Sajid is presenting. So,
Yes, ma'am. Yes, ma'am.
I shared it, ma'am.
Sir, we can see your poster. We can see your poster.
I am Dr. Sajikumar from Department of Physics, Christian College, Katakada, Trivandrum. Growth and characterization of bis thiourea zinc nitrate crystal. Some throat pain, so some sound. I have grown bis thiourea zinc nitrate crystal. Metal abstract metal complexes of thiourea are is an interesting semi-organic materials result in a stable high optical non-linear applications in optoelectronics. So for non-linear optical property, I grow this thiourea zinc nitrate crystal. This is the grown crystal, and the structure of this crystal was confirmed as orthorhombic from the X-ray diffraction pattern. The WH plot for Xrd data is also taken, which gives the elastic properties of this bis thiourea zinc nitrate.
Sure, ma'am. Sure, ma'am. Okay, ma'am. Sure, ma'am.
Thank you, ma'am. We came to the end of the day one. In this junction, I express my hearty thanks to our chairpersons, Dr. KPV Shabari sir and Dr. M. Prada ma'am, for your presence in this session. And also like to thank poster presenters and also the participants for this session. Thank you for all. As per the schedule, day 2 session will start 10 a.m. and the list of oral participants be ready with your presentation. Any doubt how that, please contact us. We will meet you next session. Thank you for all.
Thank you, ma'am. Ma'am, I am Dr. Saji Kumar. Due to network problem, I can't proceed, ma'am.